In this video, I'll talk about ways to prepare alcohols via substitution and addition reactions. So first up will be an SN2 reaction. The SN2 is going to require either primary or secondary substrate, and it requires a strong nucleophile. Given that we're trying to install an alcohol group in, something like NaOH would be a very common nucleophile to use. So this first reaction I'm going to show here, we have 1-bromo-propane will react with NaOH. So we got a strong base here on a primary substrate to give propyl alcohol. This also works again on a secondary substrate. It just won't be as fast as it is on a primary. Again, the hydroxyl group comes in, bromide kicked out to give your alcohol. So that's SN2. You can also prepare alcohols via SN1 reaction. In this case, though, you need either a secondary or tertiary substrate and a weak nucleophile. So often, water is used as the nucleophile. Now notice both SN2 and SN1 can use a secondary substrate. The nucleophile that's used is going to determine whether it's SN1 or SN2. If you use hydroxide on a secondary substrate, you'll get an SN2 mechanism. If you use water on a secondary, you'll get an SN1 mechanism. So for this example, I've got a tertiary substrate. The iodide leaves to give a tertiary carbocation, and then water comes in. The water will undergo deprotonation to give your final product. So next up will be the addition reactions. And the first of these addition reactions is acid catalyzed hydration. This proceeds via Markovnikov addition. So the alcohol or hydroxyl group will add to the more substituted position. So in this reaction, I've got sulfuric acid. Right, you can think of this just as H plus as a strong acid, and then water. So the electrons in the pi bond come to that proton. The hydrogen adds to the more substituted position, leaving a secondary carbocation here. Water then comes in. And then it will be deprotonated by a water molecule to give H3O plus, and then your alcohol. Now, one other thing to note is that with acid catalyzed hydration, you can undergo carbocation rearrangement. So that's just something to keep in mind. You may get a mixture of products depending on whether your substrate is one that can undergo that rearrangement. So that's why there's another addition reaction, oxymercuration, demercuration, where you will not undergo carbocation rearrangement. The mechanism for this, we first form our cation. So we've got mercury with two acetates bonded to it. One of these acetates leaves. So this leaves you now with your mercury cation. So I'm going to use the same alkene from last time. This will react with that cation. And I have my carbocation now. The lone pair on the mercury will then attack that carbocation. So I'm left with the mercurium ion now. Now my nucleophile comes in. I'm using NaOH in this case as the nucleophile. So I've just added that into the solution now. Comes in and kicks off that mercurium ion. So I have my alcohol now. And the mercurium. Then what I use is sodium borohydride to take the mercury off. So that would be the demercuration step. And now I'm left with my final product. Same one we got with the acid catalyzed hydration, but this time you'll never undergo a carbocation rearrangement. Now if I want to get anti-Markovnikov addition, I need to use hydroboration oxidation. Now the mechanism for this is very complicated, so I'm not going to put in that mechanism. In my experience with organic 1 or 2 class, you need to know what hydroboration oxidation is going to do, because it's very important in terms of it's your way to get anti-Markovnikov addition of an alcohol. But the mechanism itself probably isn't something that you'll need to learn. So I'm going to use my same substrate again. The reactants with the hydroboration oxidation, we got step 1, and then step 2 we got hydrogen peroxide and NaOH. And I form now an anti-Markovnikov addition. So here I've got a primary alcohol, whereas I got secondary alcohols with the previous 2 reactions. The next addition reaction I'm going to go to is one where you add 2 hydroxyl groups. So first up is going to be antidihydroxylation. So in this reaction, cyclohexene as the substrate. The cyclohexene will react with a peroxy acid. So notice the peroxy acid is like a carboxylic acid, but it has an extra oxygen on it, so it's even more reactive. The electrons from the bond between the oxygen and hydrogen attack the pi bond, and the pi bond electrons in turn attack that hydrogen. Then the bonds from there move over, and these bonds over to the hydrogen. So a lot going on there. So what I get then is a carboxylic acid as a byproduct, and now an epoxide. Right, notice all the bonds to this oxygen have been broken, except for now the new bonds between the oxygen and the cyclohexene. Okay, so now that I have the epoxide, it'll react with an acid so the lone pair will take one proton. So the epoxide is now protonated. It's even more reactive than epoxides already are. Now I'll have water come in. We have no hydroxide, right? We're in an acidic solution, so water will come in. Because the oxygen is facing, in this case, the top side of the ring, to get the backside attack, we have to come underneath the ring. So the water that just attacked the epoxide is on the opposite side of the ring. Right, then we undergo deprotonation with water to give the anti-product. So in the anti-dihydroxylation, there's two common peroxy acids that are used. One is peroxyacetic acid. A second is something called MCPBA. In the structure of the MCPBA, we have a phenyl group with the chloride in the meta position, so metachloride. That's what the MC stands for, and then we have the peroxy acid part. So those are two common ones that you'll see used in this reaction. The last addition reaction is going to be syn dihydroxylation. So I'll use the same substrate I used for the anti. In this case, it's reacting with an osmium compound. Come and attack the oxygen, the electrons move over to the osmium, and then electrons from the double bond here go to the other end of that pi bond. So this gives an intermediate known as a cyclic osmate ester. So it's similar to an epoxide in that these are bonded to the oxygen. It's similar, but it's bonded to two oxygens, not just one, right? Then a base, either of these bases are common to use. So you have that, or that with water, that will take off the osmium, and you're left with now 1,2-dihydroxycyclohexane. So these are all the common addition and substitution reactions that you'll see in the preparation of alcohols. The next video, I'm going to go over preparation of alcohols using Grignard reagents.